Good morning, dear friends. Welcome to 21 CE. Let's solve October-November 2023 paper 4, past paper, IGCSE Physics. Yes, okay, let's solve the question. So the first question is about density. Oil density 0.80 gram per centimeter cube is poured gently into the surface of the water. Density 1 centimeter cube. Okay, oil and water do not mix. Describe and explain the final position of the oil relative to the water. So the oil will float above the water. That's the answer. Oil will be floating above the water. And explanation, because the oil has less density than water. Oil is less denser than the water. Okay. But we have to source some evidence also. So we have to use the values here. So in this marking scheme, they didn't mention values, marks for values, but usually they'll give marks for values. So it's better mention values like 0.80 gram per centimeter cube is less than 1.0 gram per centimeter cube. An irregularly shaped solid object has a density of 2.7 gram per centimeter cube. Describe a method to measure the volume of the irregularly shaped solid object. So how we will measure the volume? So we'll take a measuring cylinder and then we'll fill with water. We'll note how much volume the water occupies, water or any liquid for that matter, and then we'll put the uh, irregularly shaped object. So the water level will increase. So this amount of increase volume is the object's volume. Okay. So using a measuring cylinder, partially fill the measuring cylinder with the liquid and measure the volume and submerge the object. Difference in the volume is object's volume. Nice. Okay, third part of the question. The volume of the object is 83 centimeter cube, and they gave the density of the object also 27 or something. Calculate the mass of the object. We know that density is mass by volume. We have to find the mass. So rearrange the equation. Mass is density into volume. We know density is 2.7 gram per centimeter cube, and volume is 83 centimeter cube. So we just have to multiply both to get the mass. 22.7 into 83 gram. So 224.1 gram. So here I didn't convert to standard SI unit. So we can just give the answer in grams. If you just write 2 to 4, it's not valid. You have to write 2 to 4 grams, 224 grams. Otherwise, 0.22 kilograms that you can write. Yeah. Okay. First question is done. Nice. Next question. Okay, figure in the graph shows extension of a spring varies with the load suspended from it. Determine the spring constant of the spring. So they gave one value for load and then the corresponding value for the extension. We know that the spring constant equations F equal to K into X. Spring equation. K is F divided by X. So we'll take the force as load. Load is the force. 14 Newton divided by 4 centimeter. So the answer will be 3.5 Newton per centimeter. Okay, so that's answer 3.5 Newton per centimeter. Okay, next part of the question. Same graph, same. Mark the limit of proportionality and label this point L. So what is the limit of proportionality? Until which the elastic deformation will happen. Meaning that if you apply the load, it will elongate or compress. If you remove the load, it will come back to its original position. So that limit is until this straight line. So where the curve starts is plastic deformation. So limit of proportionality is end of the straight line. So that's our limit of proportionality. Yeah. No. Okay. Next part. Okay. Different topic with the same question. Figure shows a car traveling at a constant speed along the corner A on a road. First, on figure 2.2, mark with the arrow direction of the resultant force acting on the car as it travels around the corner A. So now it's travel around the corner A. Okay, so it's going in a curved shape. So in order for the car to turn around, it should have a centripetal force that is towards the center, okay, center of the circle. Even though there is no circle, we can see that the road curvature can form a small circle here. So the force, resultant force will be towards the center. So it will look like this. Okay, so it's an imaginary center. It's not nothing actually there. Okay. Second, corner B has a smaller radius than corner A. The car travels at the same speed around the corner B as around corner A. State how the resultant force changes due to the car traveling around a around a corner of smaller radius. So the force will increase. The more change in the direction requires more force. So the force increases. That's all. Okay. Can move to the next question. Figure 3.1 shows a boy throwing a ball at an object in the fairground. Okay. The ball has a mass of 190 gram and travels horizontally with a constant speed of 6.9 meter per second. Calculate momentum of the ball. What is momentum? Mass times velocity. So momentum is mass into velocity. So mass is 190 gram. So here we have to convert into SI unit. So I am using 0.19 kg and 6.9 meter per second. Okay. So 0.919 into 6.9. So that is 1.31 kilogram meter per second. Okay. So this you can write it as a, yes, just write it as 1.31 meter per second. That's all. Okay. Okay, let's move to the next question. No, same question, second part. After hitting the object, the ball bounces back along the same straight path. So it goes like this and it hit the object and bounce back in the same direction. With the speed of 1.5 meter per second. The object has mass of, so this object, stationary object initially has 1.8 gram. So that the bowling, I guess. Calculate the speed of the object after it hit by the. So what happens? It comes with some speed and it hit the object, and this object stops moving with some speed, and this ball bounces back with 1.5 meter per second. So we have to calculate this speed. So we have to use we can use the conservation of momentum concept to find the velocity of the object. Okay. So the total initial moment must equal to the total final momentum. So not momentum. So we can form this equation m1u1 plus m2u2 equal to m1v1 plus m2v2. M1 means mass of the ball, M2 is mass of the object. U means initial velocity, V means final velocity. So U1 and U2 are initial velocity of the ball and the object. V1 and V2 are final velocity of the ball and object. Yes. So M1, U1 we have found in the last part. Okay, so I maybe I'll put in this one here. Okay, so the momentum of the ball, initial momentum of the ball plus initial momentum of the object is equal to final momentum of the ball plus final momentum of the object. We just found the initial momentum of the ball as 1.3 and initial momentum of the object is 0 because initially it's stationary. V is 0. So it doesn't matter what mass it has, its momentum is 0. So the final, to take the final momentum of the ball, so you have to take the direction also into account. Velocity is a vector, okay? So initially we consider this as plus value. So when it bounces back, this will take as a minus value because your reference is this direction, positive. So when you come back, it's negative. So that's why this 1.5 meter per second is in minus. So minus 1.5 multiplied by the mass of the ball, 0.19 kg, plus the final velocity, V0, V object, final velocity of the object, multiplied by its mass, 1.8 kilogram. Okay. So all we have to do is rearrange this equation for V, final velocity of the object. So this 1.3 stays in the left hand side and minus 1.5 multiplied by 0.19 is 0.28. That is minus 0.28. If it goes to that side, then it comes plus. Then totally divide by the 1.8. Okay. So if you work out the numerical, then it will be 1.58 divided by 1.8, which is 0.88 meter per second. So that's the final velocity of the object, 0.88 meter per second. Okay, next part of the question. The kinetic energy of the ball is 4.5 joule before the collision and 0.2 joule after the collision. So calculate the change in total kinetic energy of the ball and the object during the collision. Okay, the question looks like a little complicated, but it's not. So what they're asking, calculate the total change in total kinetic energy. So how we can calculate? So total kinetic energy before, meaning that the initial kinetic energy of the ball plus initial kinetic energy of the object. Okay, that's the total initial kinetic energy. What's the difference between total final kinetic energy? What is total final kinetic energy? The final kinetic energy of the ball and the final kinetic energy of the object. Okay, so total kinetic energy is same as the just kinetic energy of the ball, because initially the kinetic energy of the object is zero since it's not moving. Yes, and we know that kinetic energy is half mv square. So initial kinetic energy is just 4.5 joule. Kinetic energy is half mv square, and final kinetic energy of the object. We know the final velocity of the object we just found as 0.88. So we have to use in this equation half mv square. Then we can find the final kinetic energy of the object. So just half into mass of the object is 1.8 and velocity we just found out as 0.88. This is final velocity of the object square. Okay. So if we do the numerical, we get 0.69 joule. So the total final kinetic energy, okay, so this will be 0.69 joule plus the ball's kinetic energy, which is 0.2 joule. So this is final kinetic energy, total final kinetic energy. It's 0.9 joule. So the difference in the energy is, so initially we have 4.5 joule, finally we have 0.9 joule. So the difference is 3.6 joule. So this is the change in the kinetic energy. So this much energy lost during this collision. That's what you have to take in account. Okay. So 3.6 joule. That's our answer. Change in the kinetic energy. Yeah, we can move to the next question. Thermodynamics. The lowest possible temperature is 0 Kelvin. Yes. State the name of this lowest possible temperature. This is called absolute zero. So that's the answer. Nitrogen boils at 77 Kelvin. Calculate the boiling point of the nitrogen on the Celsius scale. So how to convert Kelvin into Celsius? We know that Kelvin, so that's we know the formula. Kelvin is degree Celsius plus 273. Yes, so now it's given in Kelvin. If you want to convert, what we have to do? Degree Celsius is Kelvin minus how much in the Kelvin minus 273. Okay, and yeah, Kelvin given, it's given as 77 Kelvin. So in degree Celsius, 77 minus 273. So this minus sign in the degree is very important. 196 degrees Celsius. Okay, and you should never put a minus sign before Kelvin. So it doesn't mean anything, because the minimum temperature is 0 Kelvin. That's all. Okay, there is no Kelvin beyond that. Okay, next part of the question. The temperature of a fixed mass of a gas at a constant volume changes from 300 Kelvin to 400 Kelvin. State and explain in terms of particle the effect of the effect on the pressure of the gas. So the volume is not changing, constant volume and fixed mass, just the temperature increase. So what will happen? The pressure on the gas will increase. So pressure of the gas will increase. Why it increased? So theoretically, one reason, PV is proportional to T. Okay, pressure into volume is proportional to temperature. If you keep one constant and increase either pressure or the volume, the temperature will increase. Okay. What's the second reason? The if you increase the temperature, the average kinetic energy of the particle increase. So they vibrate faster, they move faster. They move faster means more frequent collisions, faster collisions. Okay, so where do they collide? On the wall. So that's what pressure. Okay, force exerted by area, right? So more particles collide means more force. More force for the same area is more pressure, since pressure is force by area. That's all. So the keyword is more frequent collisions, more faster collisions on the wall, and collide with more force on the wall. This 3 contains 3 mark, and pressure on the gas will increase, contain 1 mark. So totally 4 marks. This PV proportional to T was not awarded mark in this marking scheme, but in general they will be awarded. It will be awarded marking scheme. Yes. Okay. Next part of the question. A sample of gas is at a pressure of 120 kilopascal. The volume of the gas is doubled at the constant temperature. Calculate the new pressure of the gas. Okay, we can use this equation. P1 V1 equal to P2 V2. Okay, if you increase or decrease the volume, the pressure will change. If you increase the volume, pressure will decrease. If you decrease the volume, pressure will increase. Okay. So now P1 is 120 kilopascal, and V2 is twice as V1, double the V1. So this is the data given. We just have to rearrange the first equation to get V2. So P2 is P1 V1 divided by V2. Okay. Sorry, not V2. We have to find P2, pressure, new pressure of the gas. Okay. So 120 instead of kilo, I just put 10 power 3 into V1. Let's keep it V1, no need the values, because denominator also we are using twice V1. So the numerator V1 and denominator V1 will get cancelled. Pascal. So 120 divided by 2 is just 60. So it's 60 into 10 power 3 Pascal or 60 kilopascal. This is how you can keep it. Okay, nice. Let's move to the next question. Okay, waves. So figure 5.1 is a scale diagram of wavefronts of red light approaching a gap in the barrier. Draw 3 wavefronts after the wave has passed through the gap. So one important thing that we have to note whenever we draw the wavefront, that the straight lines were given, right? We must draw the wavefronts exactly same as this gap. Okay. So they asked for 3 wavefront. Even if they didn't ask for 3 wavefront, it's good to write draw 3 wavefronts. Usually the marking scheme contains for 3 wavefronts 1 mark, like that. Okay. So even like we know that we are drawing it by hand in the examination. So even if you cannot draw it exactly as equal gap as earlier, you can just indicate a small arrow mark indicating that this is wavelength of the wave. Okay, both are same. This will give you mark. Even though like not to scale, you just indicate that these are same wavelength. Okay, let's move to the next part of the question. So it's the same barrier and gap. Okay, the gap barrier width hasn't been changed. It's not been changed. A wave of blue light approaches this barrier. So initially it was red light, now it's blue light. Draw 3 wavefronts before it reaches to the barrier, and draw 3 wavefronts after the wave passed through the gap. So first let's draw 3 wavefronts before reach. Okay. The blue has shorter wavelength than red. So it must be shorter than these 3. Okay. Sorry. Okay, so the wavelength is shorter than the red light, meaning that it's higher frequency than the red light. Higher frequency means more energy. So more energy means less diffraction. Okay, so shorter wavelength means shorter diffraction. This is how you can remember. So initially we draw, they were widely spread. Okay, now we will draw like it hasn't spread that much because of shorter wavelength. Okay, so little more flat. This is how we can draw. Still you have to mention that this is same wavelength. Okay, I hope I'm clear on this one. Shorter wavelength means shorter diffraction. Also wider gap means shorter diffraction. Okay, yes. Now let's move to the next part of the question. Sorry, we'll just mention this is wavelength. Yes, next part of the question. Sorry, next question. Electricity and magnetism. On figure 6.1, sketch the current voltage graph of a filament lamp and explain its shape. Okay, let's label the axis. So you can actually label anywhere on I in the y axis or V in the x axis. In general, this is called IV curve. So Let's put I in the y-axis and V in the x-axis. Okay. So what happens in the filament lamp? As you increase the voltage, we know V equal to I into R. Okay. So resistance will also increase because more current will increase, so the temperature will increase. If the temperature increase, the resistance will increase. Okay, so this is how the graph will look like. So for higher voltages, you will have more or less like saturated current. Okay, so why? As current increases, temperature increases, so resistance also increases. So more voltage is required for same increase in the current. As you increase the voltage, more and more current. Okay, let's move to the next part of the question. Source and electric circuit. Calculate the reading on the voltmeter. Okay, so this gives 2 marks for the trick. There is no mathematical thing here. So they have connected two batteries back to back, 12 positive, negative, and then negative 3, positive 3. Okay, so which is the higher voltage? 12, so it will dominate. So this plus and minus, the minus. So 12 minus 3. Okay, so the voltmeter will show 9 volt. So whatever the volt in the battery will be shown in the voltmeter, 9 volt. Okay, only for this trick, there is one. Yes. Calculate the current in the 4.2 ohm resistor. Okay, so there are two diodes that must be noticed. The 4.2 ohm diode is in the forward bias. You know which is the direction of the diode, only in that direction it will work. Okay, so the back side of the diode, which is positive, has been connected to positive, and the sign of the batteries, which has the higher voltage, that sign will be applicable to the battery. Okay, that we have to take. Yes, so we know that V equal to IR, I equal to V by R. So the voltage is 9 volt and then the resistance is 4.2. So 9 divided by 4.2, which is 2.1 ampere. So 2.1 ampere is the current in the 4.2 ohm resistor. Okay, next comes a little trick question. No work required, just trick. Determine the current in the 2.1 ohm resistor. So if we have a bad day, we will calculate using same formula, V equal to IR, I equal to V by R. If we are thinking, just thinking that the diode in front of the 2.1 ohm is in the reverse bias, it will not allow the current from positive terminal of this battery. So no current, zero current. Okay, determine the reading on the ammeter. So only one resistor is connected to the circuit. That resistor's current we found as 2.1 ampere. So the other resistance will not conduct any current because the diode is the reverse bias. So the 4.2 ohm current is the total current in the circuit. So we will get 2.1 ampere. That's all. Nice. Okay, next part of the question. Calculate the electrical power transferred in the 4.2 ohm resistor. So what's power? Voltage into current is power. So voltage we have 9 voltage and current is 2.1 ampere. If we multiply, we get 18.9 watt. We can round it up to 90 watt. You can calculate I square R also. We'll get the same result. Yes. Okay. Next question. Okay. Charges. Figure 7.1 shows the electric field pattern around point X. Okay, on figure 7.1, draw an arrow to indicate the direction of the force of a negative point charge placed at point Y. So this also answers the second part of the question. Okay, so the X arrows are pointed outwards, meaning that it is a positive charge there. Okay, so the Y is a negative charge. So they will attract each other. So the direction of the force in the Y is towards the center of the X. That's how we have to draw. Okay. Second question. State what is the point, what is at point X? Okay. If you write simply positive or positive charge, still you will get 1 mark. But look at the first statement, negative point charge. Similarly, we have to write positive point charge. Then you get a full mark. It's a positive point charge. For a positive 1 mark, point charge 1 mark. Since it's a point charge only, it look like gradient. Okay. Yes. Let's move to the next part of the question. A piece of plastic is charged positively by friction. State what charge transfers occur during this process. So how a neutral material can become positive? Only if the electrons move from them, move away from them. So the electron have moved from the plastic, so it becomes positively charged. That's how you answer. Explain how the structure of an electrical conductor differs from the structure of an electric insulator. What's the difference between conductor and insulator? Conductor has more number of delocalized or free electrons. Insulator does not have. That's the only difference. So conductors have more number of free electrons and insulator does not have a free electron. That's all. Okay. Figure 8.1 shows the single turn coil of a simple direct current motor. It's a DC motor. Ex Explain the direction of the turning effect as seen by the observer at O. So this observer at O is just looking front, okay? To his left, south pole, and to his right, north pole. Okay. So what's the direction of turning? Remember that the current is going inside. Okay. So the current is going inside the direction, which direction it has to rotate. Okay. So the magnetic field from north to south. So it will go like this. Yes, we can take like this. Okay. So the direction will be up at south. Okay. So the coil rotate clockwise, plumbing right hand we can take. So this is the direction of the force. Okay, this is the direction of the current. So it goes up. So the force is upward on the left side of the coil and downward. Okay, you can take like this. Downward on the right side of the coil. Yes, sir. So not by left hand. Okay, like this you can take. Okay. Yes. So any one part if you write, we get the full mark. The coil is replaced by otherwise identical new coil with 3 turns of the same current in the coil. State how the turning effect compares with the turning effect in one. So same current, but three loops. So what happens? You are cutting more wires are cutting the magnetic field. So you will exert more force. So turning effect is greater. Okay. Sorry, it should not be more force required. It gives more force. It's a decent matter. Yes. Okay. Second, a third coil is identical to the coil in one, except its resistance is 3 times greater. The potential difference across the coil is same as potential difference across in one. Said how the turning effect compares with the turning effect. So it will have less turning effect than one because of the more resistance. More resistance means less conductivity of the electricity, meaning that less force. Okay, turning effect is less. Yes. Okay. Sorry for the mistake. More force, not more force required. It exerts more force. Okay, let's move to the next part of the question. Figure 8.2 is a voltage time graph showing the output of a simple alternating current generator at a times T0, T1, T2, T3. Okay. Figure 8.3 shows end view of the plane of the coil of the generator at time T0. The coil is rotating clockwise. So let's put this diagram. This is a clockwise position. Okay. Coil is rotating clockwise. So instead of A, I just put an arrow mark. Okay. Let's see what they're asking. Draw an end view of the position of the plane of the coil at time T1. Include the labels A and B. Okay. So initially the coil was like this. In T1, if you look, the voltage is maximum, meaning that the magnetic field is cut perpendicular. Okay. So if the field is like this, you will cut it like this. Perpendicular to the field. So which position is perpendicular to the field? So like this. So this is a position we have to draw. So B is the cent, A is the 10. Okay. Second, draw end view of the position of the plane of the coil at the time T2. include the labels A and B. So in T2 it's 0, meaning that we are cutting the magnetic field parallel, not perpendicular. Okay. So for example, magnetic field is like this. If the wire is cutting like this, means no voltage will be produced. Yes. So when the wire cut like this, maximum voltage will be produced. That's what in the first question. Now it cuts parallel. When it will cut parallel, when it comes to the position. Okay. So it will look like this. See. So in this position, it won't cut. Sorry, it will cut parallel. So the voltage is 0. Okay. Let's move to the next question. Draw an end view of the position of the plane of the coil at a time T3. Okay, from here T3. So yeah, T3 will be same as the earlier point, not at T1, next at T1. We'll see. So you go like this and then go like this for 0. Again go like this for T3. Okay. So A is in the left hand side. Then 3 marks you got. Okay, let's move to the next topic. Okay, so nuclear physics. For each application of the radioactive isotopes, state and explain which type of the radioactive emission is suitable and suggest an appropriate half-life of the isotope. Okay, first, household smoke alarm. Type of the radioactive emission. So we have to use alpha radioactivity, radio emission. Okay. Oh, sorry, should have come by point. Okay. So why alpha? Alpha particles will has not good in penetrating long distance. Okay, they'll not penetrate even small particles. So smoke particles, when they enter, it's blocked by it's blocking the alpha particle. So what actually they'll do, they'll make a small circuit. So this alpha particles will be connecting both ends of the circuit. When there is smoke particle, it will stop the connectivity, so smoke alarm will go on. Okay, so this is the reason how alpha particles works on the radioactivity. And how about the half-life? More half-life mean I do not need to change the radioactive source more often in the smoking alarm. Yeah. So one more benefit of using alpha particle is, since it's not very ionizing and not penetrating for long distance, it will not affect the humans. Okay, in the long range. Yes. Okay. Next question. Measuring. Sorry, same application for measuring the thickness of aluminum strips. This we should use beta radiation, because the beta radiation, okay, if you pass by the aluminum, the count rate depends on the thickness of the aluminum. Yes, okay. So the beta particles absorption depends on the thickness of the aluminum. uh, okay, so about the half-life period, the previous question also, it's just mentioned 10 to 500, anywhere between 10 to 500 years. For this question, marking scheme says any half-life period, so you do not need to worry. So for my sake, I put 20. Okay. Yes. Okay, let's move to the next part of the question. Lead 208. Okay, so 82 proton 208 mass number has the highest nucleon number of the stable isotope of lead. Explain why lead 214 is radioactive. So what they are saying is, if the nucleon number of the lead is 208, that's the maximum nucleon number it can have in the stable format. So if nucleon number increases further, it's unstable, meaning that the nucleons number will try to reduce to the 208. How they will reduce? By emitting any one of this radioactivity. Okay. So 214 has more number of neutrons than the stable form. So it has to reduce, somehow it has to bring. So this radioactive will reduce the number of neutrons. Okay. So depending on the radiation, this will go, I think, yeah, beta radiation, beta positive. Yeah, okay. I guess I'll check. So in general, radioactive decay decreases the number of nucleons, right? So it can come to the positive form, stable form. That's the idea. State two different sources of background radiation. There are many sources of background radiation, such as cosmic ray, rocks, radon gas. You can mention anything. Even building emits radiation, but very small amount. Okay, next part of the question. Astronomy and astrophysics, space physics. State what is represented in space physics by the symbol H naught. So H naught is Hubble constant. Okay. Write down the equation that defines H naught in terms of the speed that of our galaxy is moving away from the Earth and its distance from the Earth. We know that H naught is V by T. Velocity is velocity of the moving galaxy, relative velocity, and D is the distance between the galaxy and the Earth. Okay. The numerical value of H naught is 2.2 into 10 power minus 18. State the unit of H naught. Okay, let's calculate from, if even if you don't know the unit, let's calculate from the equation. So it's V by D. V is meter per second. D is just a second. Sorry, D is just meter. D is distance, right? So meter per second divided by meter. So meter and meter will get cancelled. You will get 1 by second or second inverse. Okay, so the Hubble constant is actually the value of frequency. It's 1 by second, right? Dimensional analysis. Okay, next part of the question. Use this value of H naught to determine and estimate for the age of the universe in seconds. This look like a big thing if you do not know the secret. That the secret is age of the universe is 1 by H naught. That's all. That's why it's a H naught constant, Hubble constant. Okay. So 1 by H naught is age of the universe, which is 1 divided by 2.2 into 10 power minus 18 second inverse. If you do the math, it's 4.5 into 10 power 17 seconds. So some 13.8 billion years in seconds. Yes. Okay, I think this is one more part is there. 4.5 into 10 power 17 second. The next part of the question. State when cosmic microwave background radiation was formed and where we detected. So CMBR was formed right after, shortly, the Big Bang wave, okay, or birth of the universe. And you receive this cosmic background radiation from all the direction and all the point of the space. Okay, I think this is the last. So there is a small interesting story about this CMBR. In search of a good design for a microwave oven. Okay, so those scientists found out other than microwave, so there is a radiation from everywhere. For that, they got Nobel Prize. Yes. Okay, I think that's it. Yeah, see you in the next question playlist. Bye bye. Thank you. 21C. Hari and Comedy. Peace.